Let us look at a particle that is moving around a circle with velocity v along the circumference. So this is the radius r and the particle is moving tangentially with a velocity v. After a small instance of time, the velocity v of the particle turns. Currently we are assuming the velocity to be constant. So the radius vector that is perpendicular to the velocity vector also turns by an angle, small angle d theta. So we are taking differential limits, or we are dealing with infinitesimally small quantities. So essentially amount of time that has passed is dt. In dt amount of time, the velocity vector has changed from initial velocity vector to final velocity vector. So if we were to find out the change in velocity, then we would have to draw the vector diagram of final velocity that is pointing like this, and we would have to draw negative of initial velocity. So this is equal to the final velocity vector, and this is equal to negative of the initial velocity vector. Okay, so the net change is final minus of initial. That is the reason why we have inverted the initial vector. So intuitively we can understand that the resultant is going to point towards the center. So this can also be constructed in this very diagram by extending the final velocity vector and extending the line of the initial velocity vector. So the change, which is final minus initial, is going to be pointing towards the center of the circle. Okay, so essentially we would like to find out the magnitude of the change. For that, it is important for us to understand that this particular angle, let us say if I extend this vector, then this particular angle, this angle also happens to be equal to d theta. The reason for that is you get a quadrilateral that looks something like this. So essentially it is a kite wherein this angle is 90 degree, this angle is 90 degree, this angle is d theta. So this angle is going to be equal to 180 minus d theta, and then this angle is also going to be equal to d theta. So this angle happens to be 180 minus d theta in degrees, or 2 pi minus d theta as measured in radians. So to find out the net change in velocity vector, or rather the magnitude of the net change in velocity vector, what we need to do is we need to write down v final minus v initial's magnitude. So I am abbreviating this as magnitude of delta v vector. So this is going to be equal to under root of v square plus 2v into v into cos of 180 minus d theta. This is what it is going to amount to. So this comes out to be, so therefore the magnitude of delta v vector comes out to be equal to, v can be taken common outside the under root sign, 2 plus 2 cos of 180 minus theta is minus of cos theta. So 2 plus 2 into minus cos theta. Okay, so this will be equal to v under root of 2 1 minus cos of d theta. Now we can use the trigonometric identity which says that 1 minus cos of d theta is going to be equal to 2 sine square d theta by 2. So this is equal to v under root of 2 into 2 sine square d theta by 2. So this is sine of d theta by 2 the whole square. So if we do take the root of this equation, we get 2v sine of d theta by 2. So this is the exact answer. Even if the angle were finite, this equation will give you the exact answer even in case of a finite angle d theta. However, here we are dealing with infinitely small angles, so in the limit that d theta tends to 0, we know that sine of d theta by 2 can be equated with d theta by 2. This is approximately equal to d theta by 2 as theta is small, and when theta is infinitesimally small, we can exactly take them to be equal in the differential limit. Therefore, this delta v is going to be written as 2v sine of d theta by 2. Instead of that, we are going to write d theta by 2. So 2 gets cancelled and we effectively write v d theta. So this is equal to v d theta. So now that we have delta v as v d theta, we can find out delta v divided by delta t in the limit that delta t tends to 0. So this is going to come out as v d theta by dt. D theta by dt we already know is the angular velocity vector or the omega vector. So this is going to come out as v omega. So basically what are we saying? We are saying that the change in velocity whose direction is pointing towards the center divided by change in time, that means the acceleration that is directed towards the center in the limit that delta t tends to 0, it happens to be the instantaneous radial acceleration. So this happens to be AR. So AR is coming out to be equal to V omega as far as magnitude is concerned, and as far as direction is concerned, it is directed towards the center as is shown in this vector diagram over here. So AR is nothing but V omega. Also, we understand that arc length is equal to r into theta, where theta is measured in radians. So ds by dt, the rate at which arc length is covered, is r d theta by dt. So this is nothing but velocity or tangential velocity v. This is going to be equal to r omega. So if we do make these substitutions, then radial acceleration also comes out to be in magnitude omega square r, and it also comes out to be equal to v square by r. So these are the expressions for the radial acceleration written in scalar format that one needs to remember.